Hey everybody, welcome to another week. We're going to start off here by doing a 4.1 through 4.3 checkpoint mix, and I think what this video is going to end up being is something you can check after you give this a try. You can check your answers, get unstuck from something. But anyway, I just got done doing some integrated math 1 stuff, so I gotta make the leap to unit 4 AP Calc BC here, so bear with me. So let's see what's going on here. So number 1, tell whether the series converges or diverges. So does this infinite sum actually add up to something, or does it just diverge to infinity or negative infinity, right? Eventually. Or it just keeps blowing up, right? So what you can do here is you can kind of analyze this general term, and we know that unless the terms actually approach 0, then the sum has no chance of converging. You know what I mean? For the infinite sum to have any chance of converging, the terms themselves have to be approaching 0. So when you actually take this limit, which you guys have been doing ever since you first met Mrs. Clute, or not first met her, but you know what I mean. You just take this limit, and since we got something that was not 0, then we automatically know it has to diverge. It has no chance of converging. All right? Or, another general strategy with questions like this is you can analyze, the partial sums. You can kind of analyze how this sum keeps updating itself for every additional term you add, right? Kind of like how I thought to try here. Number 2 is actually a dumpster fire for us right now. I mean, at the end of the day, number 2 for us at this point in time for us is kind of a bad question. But hey, you know what? It's a good learning experience, because here's what we do. I thought to analyze the partial sums. Obviously it starts off as -2, and then when you add the next term, you end up with that. And then when you add in the next term, you get that. And then you get this running sum, which it's not I'm not getting any conclusive evidence here one way or another, whether this sum is converging to something in particular or it's diverging. That's why I have this right here. I mean, analyzing the running sum, it's not clear what's going on. So we actually take this limit, okay? And just like Mrs. Clute taught you, seriously, Mrs. Clute taught you this, as well as me, kind of, the limit of this general term equals 0. Now, I know this is why number 2 is a bad question for us right now. I know this seems hard to believe right now, and it seems really weird, but if the separate individual terms are limiting to 0, that doesn't necessarily mean anything. Again, I know that sounds weird, but just because this limit actually equals 0 and we're getting closer and closer and closer to adding 0, you know what I mean? That doesn't necessarily mean that the infinite series, the sum, converges. So basically in number 2, we don't have enough, I haven't taught you enough at this point in time to actually figure out number 2. But it was a good investigation. I mean, the actual work was productive, to investigate the partial sums, or maybe you did this and you thought it converges, and now I'm like completely bursting your bubble by kind of throwing that plot twist at you like something brand new. But anyway, sorry. Number three. Here's the deal with number three. You look at this series, and I hope you realize that it's geometric in nature. You know, starting in like section 4 and section 5, we're actually going to learn a whole like bunch of ways to figure out like, does a series converge or not. They're called tests, you know what I mean? And I'll tell you right now, one of the many tests we're going to go through in section 4 and section 5 is literally called the geometric series test. So the geometric deal is one of the first things you would go to. It's one of the first tests you should probably try. So anyway, I hope you realize and you can see that this series is definitely geometric in nature. The first term is obviously 1, and r, your common ratio, you know, the thing you're always multiplying by to jump to the next term, is negative 3x squared. And if it's, you know, and we can now figure out not only when this would converge, because remember, geometric series converge as long as the common ratio is in between negative 1 and 1. So we could figure out like I know I'm getting ahead of myself, I guess, a little bit. Or am I? I don't know. I can't keep track anymore with all these classes. But if the question wanted you to, we could totally figure out for which x values this would actually converge. And we can figure out what it converges to. It's literally a formula, you know. A1 all over 1 minus r. This is what geometric series converge to, you know, on certain intervals, right, for certain x values. But you plug in your stuff into this formula, and you end up getting that. Pause the video, go back, whatever you need to do, ask me questions, I don't know. But number 4, find a power series for this function. Well, once again, most of what your go-tos are right now is geometric, and this totally fits, you know, this geometric model, okay, right? So you look at this and go, oh, so I can think of my a1, my first term, as 2, and my r as x cubed. So with those two pieces of info, this would be, you know, at least the first 4 terms of your geometric power series, you know. Again, not every power series is going to be geometric in nature, but if it is, oh, that is really good news. Anywho, if you want to give the sigma definition, that would be a pretty good version of like the sigma shorthand, you know, because these terms go on forever. You know, 2 plus 2x cubed plus 2x to the 6th plus 2x to the 9th plus 2x to the 12th plus 2x to the 15th. It literally goes on forever. So you could write it out that way. Okay, I hope this makes sense. And this would be starting at 0. If you wanted to adjust it for starting at 1, you'd have to adjust this a little bit, but whatever. And as far as the values of x for which it converges, in other words, peoples, the interval of convergence. And remember, since it's geometric, that's really good news. We know that geometric series only converge as long as the common ratio is in between negative 1 and 1. And so here our common ratio is x cubed. Okay? Now, let me pause that for a second, okay? I just want to elaborate a little bit on that sort of concept. If you have a geometric series that you might have been given like in pre-calculus, whether it was me, definitely with me, probably with Mr. Birch as well, you know what I mean? If you would have been given a geometric series like without any x's, okay? Like that's what I'm getting at here. Without any x's, like if you would have had, I'll even write it down, you know, you don't got to write this down, but 1, 2, 4, and then 8, and then 16, right? This has an R value of 2. And so you would flat out say, this infinite sum, this as a series, does not converge because your R value does not fit this, you know, this criteria. But if you had like 1, 1/2, 1/4, 1/8, you know, where your R value was flat out 1/2, then you would say, yes, this geometric series actually converges, and you can figure out what it converges to. But when you're talking about a power series, and I get it, I was in your shoes once before, we call this a power series basically because we have x's. It's not that black and white, but you know, basically all these fancy new concepts and fancy new things, you know, the bottom line is here we have a power series, we have a geometric series that has a variable in it, right? So this geometric series, it's not like the question, here's what I'm saying. The question is not, does this converge or not? The question is, for what x values will it converge? You know, what is its interval of convergence? I hope that makes at least a little bit of sense to you, because when we proceed here, we go on to figure out for what x values will this geometric series actually converge. You put r in here, our r value was x cubed, and then you essentially like take the cubed root of everything and you end up with like -1, okay? So you end up with this because just like taking the cubed root to solve for x. Okay. Is this the next page? Yeah. Oh my god, number 7 was a doozy. Number 5, hey! This, especially once you do a little investigating, this is definitely geometric. That's really good news. So then you can figure out that your A1 is 1/3, you know, whether you can just kind of do it in your head or somehow dissect this, but I mean, when you write out the first handful of terms, I mean, the first term is going to be 1/3, you know. You plug in 0. You know, you start by plugging in 0 to get off the ground with this in your first term. Anyway, your first term is 1/3, and your R value is 2. Now look, check it out. My R value is 2. Right there, there's a deal breaker. That's why it diverges. Over here in number 6, same deal, but you figure out that your R value is actually 3/4. That will actually make it converge, you know. See this will converge, period. This one is not about like, well, when does it converge? For what x values? No, number 5 and number 6, it's like, do these series converge or don't they? And if they converge, and this one does, what does it converge to? And this, again, since it's geometric, we can definitely want to use that to our advantage, the fact that it's geometric in nature, and so that is what it converges to. And you get 4. Oh my god. Number 7. Number 7 is a doozy. I'm not going to sugarcoat this. Number 7 is about as tricky and messy, I guess is the better word. Number 7 is about as messy as it gets for stuff like this that we're going to do, I believe anyway, okay? So, Taylor, okay. So first of all, the I mean, it's messy, but I do want to put a positive spin on it as well, right? Positive spin coming at you. The whole routine with doing a Taylor polynomial, and even, even the Taylor series is sometimes easy, but at least the Taylor polynomial will always be very easy because it's a very easy routine. You take the original function, you take the first derivative, the second derivative, the third derivative. You go as far as you need to. Here we want the third order, so I went all the way to the third derivative. And then here we want the third order polynomial at x equals 0. So you simply plug in 0 to all of those. The original function, the first derivative, second derivative, third derivative, and you get your answers. And then you take those answers and you apply them as coefficients to each term in the Taylor polynomial power, whatever, okay? So the first term is x to the 0 over 0 factorial, x to the first over first factorial. It all follows a nice little procedure. X to the second over 2 factorial, and then the third factorial, okay? So all of these kind of finished off each term. And then here I just kind of cleaned things up a little bit, okay? Now, the series and defining the series, I mean, that's definitely the tough part. Gosh. You know what? This, what do I want to say first here? If you actually, see, this part of the Taylor series is actually pretty easy. You know that every single term followed this pattern and had x to the n over n factorial. What's potentially tricky is defining all the other crap that kind of joins along in with it, all these coefficients. And sometimes it's hard to dissect that. And maybe you've heard me say before the shutdown, probably not, but the more you reduce, sometimes, the more you reduce sometimes, the harder it is to know like where it all came from. You know what I mean? Maybe you can like analyze this and understand that, the 2, right? I mean, maybe I'll say this first. The fact that you had like x plus 3 to this power, x plus 3 to this power, it's probably not difficult to understand where the 3 came from and the 9 came from and the 27 and the 81. But like the 2 and the negative 2 and the 4 and the negative 12, I don't know, that's pretty difficult to realize that what that's coming from is 2 times n factorial. You know what I mean? There was always a 2, but this happened to be 2 times 1. This was also 2 times 1. This was 2 times 2. This was 2 times 6. You know what I mean? We actually had this like n factorial thing going on. And then they kind of cancel out. You know what I mean? And then check it out. It doesn't make it any easier that you need like this to be n plus 1. And then, not only that, but the terms are alternating by sign. So you also need this put in the series. Now this would be like more of a final answer. which you actually can probably look at this sort of final polynomial up here and go, oh yeah, there was a 2, and these denominators were always like 3 to a power. And we had a 2, and then it was alternating, and then we had like x to the n. Anyway, I'll move on from there, but that was definitely the trickiest part. And then part B is very, 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 very similar, except now you're plugging in 2. Alright? And you know what? Oh my god, as I look at this, oh my goodness. This is something that I forget. I'm so mad at myself. This is going to be x minus 2 in a bubble to the 1 power. X minus 2 in a bubble to the 2nd power. X minus 2 in a bubble. So, I mean right here, x minus 2 in a bubble. X minus 2, gosh, in a bubble. X minus 2 in a bubble. And so down here, guess what? This is going to be x minus 2 in a bubble to the n power. You know what? I'll give a class bonus for that because I almost didn't catch that. Anyway, I mean, so yeah, there as well, obviously, but okay. And let's try to make number 8 as easy as we possibly can. So here's the series. Turns out that it's geometric, right? That's a very good thing. Turns out to be geometric with r equaling that. And obviously that would be the first term once because you're plugging in 0 to start. So that's why you can find your interval of convergence this way, because this is r. And so this ends up being our interval of convergence. And then using this as a format, I know there's some, but this ends up being like a good final function that it represents. And the last thing I did here was I multiplied top and bottom by 2. Hopefully you don't run into that too much here. Find a power series for the derivative. Well, I want you to compare the original power series and this. All you have to do essentially is bring the n down in front and drop it down to an n minus 1, like taking the derivative. And then for the integral, same deal. You just kind of bump that power up to an n plus 1 and divide by that new power, just like you've taken integrals ever since Mrs. Klut's class. So I don't want to convolute that any more than I have to. Let's just kind of try to simplify that as much as possible. That's kind of all you need to do. Take the derivative of that and take the integral of that.